Yeah, rivers can clean themselves, and humans are making it harder for them to do so. A process called self-purification occurs naturally in all rivers across the globe. Most people believe that if you discard waste in the river, it goes with the current all the way to the ocean, but there's more to it. In this episode, we are going to see how we define clean water, understand how self-purification works, and how humanity is taking away that ability. Before talking about cleaning rivers, we need to know how to classify if a river is clean or polluted. The need to evaluate and compare data of different water bodies across different locations and time periods culminated in the creation of the Water Quality Index, or WQI. The Water Quality Index is a standardized numerical tool used to assess and communicate the overall quality of surface water. WQI models condense complex data into a single value, making water quality judgment more accessible for decision makers. The first widely recognized model was developed by Horton in the 1960s, followed by refinements such as the National Sanitation Foundation WQI or NSF WQI, developed by Brown. There are several WQI worldwide, but we are focusing on the NSF WQI for this video. It is calculated using several key physical, chemical, and biological parameters. These parameters are assigned weights based on their significance to water quality, and their values are aggregated into a single index score. The higher the score, the cleaner the body of water is. In the NSF WQI, these parameters are dissolved oxygen, biochemical oxygen demand, pH, temperature, total dissolved solids, nitrates, phosphates, turbidity, and fecal coliform bacteria. We'll be talking more about some of those parameters later. The resulting index is then evaluated based on the following ranges. 0 to 24 is very bad, 25 to 49 is bad, 50 to 69 is considered medium quality, goods from 70 to 89, and excellent from 90 to 100. While the Water Quality Index is a useful tool for assessing water quality, it has several limitations that affect its accuracy and applications. Some of the limitations include the simplification of complex data and subjectivity in parameter selection and weighing. Some WQI also exclude emerging contaminants in the likes of microplastics, pharmaceuticals, and pesticides from their calculations. There's also a tremendous regional specificity, as many WQI models are tailored to specific locations and may not generalize well. Despite these limitations, WQI remains a valuable baseline tool for tracking water quality trends, guiding environmental management, and raising public awareness. However, complementary methods such as biological assessments, satellite monitoring, and machine learning models can help improve its accuracy and relevance. Now that we have defined how we evaluate the water quality in a river, let's see how nature deals with pollution and cleanses itself through self-purification. Self-purification is a natural process in which rivers improve water quality by reducing pollutants through physical, chemical, and biological mechanisms. This process involves microbial degradation, sedimentation, aeration, and the assimilation of contaminants by aquatic organisms. During self-purification, 4 distinct zones can be identified along the watercourse, each exhibiting significant variations in biochemical oxygen demand and dissolved oxygen concentrations, as well as other substances like nitrogen and phosphorus. Dissolved oxygen indicates the amount of oxygen available for aquatic organisms, being crucial for aquatic life and water quality. Oxygen is dissolved in water from the atmosphere and by photosynthesis from aquatic plants. Biochemical oxygen demand measures the amount of oxygen that microorganisms require to decompose organic matter in water. A higher BOD indicates a greater presence of biodegradable material, which can lead to oxygen depletion in aquatic environments. The 4 zones of the self-purification process are the clear water zone, upstream of the effluent discharge point, where the effluent mixes with the water body, resulting in a new concentration termed mixture concentration. In relatively clean rivers, BOD concentrations range from 3 to 4 mg per liter, and DO levels are about 7 to 9.5 mg per liter, depending on altitude and temperature. Degradation zone, downstream from the discharge point, where the effluent disperses more significantly, leading to increasing BOD and decreased DO concentrations. The bacterial diversity diminishes due to reduced oxygen availability. Though some bacteria resistant to pollutants persist, the riverbed may become anaerobic, producing hydrogen sulfide gas. Active decomposition zone. characterized by extremely low DO concentrations, often approaching zero. Anaerobic conditions prevail, leading to the proliferation of anaerobic bacteria and the production of gases like methane and hydrogen sulfide. Aquatic life requiring oxygen cannot survive in this zone. Recovery zone. Further downstream, where natural processes increase DO levels, allowing aerobic microorganisms to recolonize and degrade remaining organic matter. The zone marks the gradual return to conditions similar to the clean water zone. Understanding these zones is essential for assessing the impact of effluent discharges on aquatic ecosystems and for designing effective wastewater treatment and management strategies. This process only applies to biodegradable materials such as organic matter. Several human activities negatively impact the natural self-purification of rivers by introducing excessive pollutants and disrupting ecological balance. Industrial discharge introduces heavy metals and toxins, overwhelming microbial degradation and accumulating in sediments, posing toxicity risks. Agricultural runoff leads to eutrophication and oxygen depletion. Deforestation increases erosion, raising turbidity and blocking sunlight for aquatic plants. Continuous sewage disposal raises BOD, straining natural purification processes. Over-extraction of water reduces flow, slowing pollutant breakdown. Plastic and microplastic pollution interferes with microbial communities and aquatic organisms. Dams and river modifications trap pollutants and alter sediment transport. Aquatic plants play a crucial role in self-purification, enhancing water quality through phytoremediation, absorbing pollutants like nitrogen and phosphorus to prevent eutrophication. They oxygenate water, supporting microbial degradation of organic matter. Their roots stabilize sediments, reducing turbidity and trapping contaminants. Certain plants, such as water hyacinths and reeds, absorb heavy metals, while others provide habitats for beneficial bacteria that break down harmful substances. Rivers possess an incredible natural ability to cleanse themselves through self-purification, a process that relies on microbial activity, sedimentation, aeration, and aquatic plant interactions. However, human activities such as industrial discharge, agricultural runoff, deforestation, and urbanization have increasingly burdened these systems, overwhelming the river's ability to recover. While tools like the Water Quality Index help assess pollution levels, they have limitations, highlighting the need for complementary monitoring methods. Understanding self-purification mechanisms and the factors that hinder them is essential for sustainable water management. By reducing pollution, protecting aquatic plants, and implementing effective conservation strategies, we can help restore and preserve the health of our rivers for future generations. Thank you for watching. Don't forget to like and subscribe to follow future videos. Goodbye.